1944. World War II is still being fought. And somewhere in Japan, a 29-year-old mathematician named Kiyosi Itô, working in near-total isolation, with limited access to Western literature, writes 4 pages. 4 pages that would eventually underpin every option, every swap, every structured product, every exotic derivative traded on this planet. $600 trillion. That's the notional size of the global derivatives market, built on 4 pages. Your calculus professor never mentioned Itô's name. I'm going to tell you why. Classical calculus, the Newton-Leibniz version you were tortured with in school, works beautifully on smooth, differentiable functions. You have a curve. You draw a tangent. You compute a derivative. Everything is clean. Everything is deterministic. Financial markets are none of those things. This jagged, violent, non-differentiable path, Brownian motion, is what actually drives stock prices. You cannot draw a tangent line on it. It has no derivative in the classical sense. Everywhere you look, it's rough. Itô's genius was building a calculus for rough paths. A calculus where the correction term isn't just a philosophical nicety. It's a trading signal worth hundreds of billions of dollars. Welcome back to Quantifea. Let's get into it. Before we can understand Itô's lemma, we need to understand what it's operating on. And that means understanding Brownian motion, the mathematical object that Norbert Wiener formalized in 1923. Brownian motion, also written B of t or W of t, is defined by 3 axioms. First, it starts at 0. B of 0 equals 0. Clean slate. Second, increments are normally distributed with variance equal to the elapsed time. The increment from time s to time t, b of t minus b of s, follows a normal distribution with mean 0 and variance t minus s. This is crucial. The uncertainty grows proportionally to time, not to time squared. That square root of time scaling is why volatility scales with the square root of the holding period, a fact every risk manager on Earth uses daily. Third, the increments are independent. Yesterday's move tells you nothing about today's move. The process has no memory. It's the financial equivalent of a goldfish. And here's the property that breaks classical calculus completely. Brownian motion is almost surely continuous. No jumps, but nowhere differentiable. Zoom into any segment, no matter how small, and it's still rough. It's a fractal. It has no tangent anywhere. Now look at this property. The expected value of dB squared, the instantaneous variance, equals dt. The square of the random increment is deterministic in expectation. This is the single fact that makes Itô's correction term exist. Hold on to it. It will become everything. Think of Brownian motion as the raw material. What Itô did was build the machinery to work with it, to differentiate and integrate functions of this chaotic object, like building a lathe to cut stone that no blade had touched before. Now here's where things get genuinely interesting, and where every student who learned calculus and thought they were done gets a very rude awakening. In classical calculus, when you expand a smooth function f of x plus dx using a Taylor series, you get f of x plus the first derivative times dx plus 1/2 the second derivative times dx squared, and so on. And as dx goes to 0, the squared term goes to 0 faster. It's order dx squared, which is negligible compared to dx. So you throw it away. That's the entire story of classical differentiation. Now try the same trick with Brownian motion. Replace dx with dB, the infinitesimal Brownian increment. You get the same expansion, f prime times dB plus 1/2 f double prime times dB squared. And here's the question that defines stochastic calculus. Can we throw away dB squared the same way? The answer is a categorical no, and the reason is in this table of orders. In classical calculus, dt squared goes to 0, fine. dt times dB goes to 0, fine. But dB squared? dB is of order square root of dt. So dB squared is of order dt, which does not go to 0. It stays. It matters. It changes the answer. This fact has a name: the quadratic variation of Brownian motion. The sum of squared increments of b over any partition of the time interval converges, almost surely, not to 0 but to t, the length of the time interval. This result, which goes by Theorem 3.4.3 in Shreve's stochastic calculus for finance, is what separates Itô's world from Newton's world. We can write this compactly as a multiplication table for stochastic differentials. dt times dt is 0. dt times db is 0. But db times db equals dt. Not approximately. Not in some limiting sense. Equals. The square of a random quantity is deterministic. Stochastic calculus is built on this audacity. And if your first instinct is that this feels wrong, good. That means your mathematical instincts are working. They're just calibrated for the wrong universe. Markets live in Itô's universe, not Newton's. Right. Gloves off. We're deriving Itô's lemma from first principles. No hand-waving. No, it can be shown. We're doing the actual proof. Let x of t be an Itô process, a stochastic process described by this SDE. dx equals mu dt plus sigma dB. The mu term is the drift, the deterministic trend. The sigma dB term is the diffusion, the random shock. Every continuous time financial model you've ever seen is a special case of this structure. The question Itô asked and answered is this: if x follows this process and f is a smooth function of x and t, what process does f follow? In classical calculus, the answer is just the chain rule. In stochastic calculus, the chain rule is wrong. And Itô's lemma tells you why, and by how much. Step 1. Taylor expand f to second order in dx and dt df equals partial f over partial t times dt, the time derivative, plus partial f over partial x times dx, the space derivative, plus 1/2 partial squared f over partial x squared times dx squared. And higher order terms. So far this looks like classical calculus. The crime happens in the next step. Step 2. Substitute dx equals mu dt plus sigma dB. Now compute dx squared. That's mu dt plus sigma dB, all squared, which gives mu squared dt squared, plus 2 mu sigma dt dB, plus sigma squared dB squared. Step 3. Apply Itô's multiplication table. dt squared is 0, negligible. dt times dB is 0, negligible. But dB squared equals dt. Watch what happens. 2 of the 3 terms in dx squared vanish, gone, and we're left with sigma squared dt. That's the Itô correction. It came from the squared term in the Taylor expansion that classical calculus told you to throw away. Except in Itô's world, you cannot throw it away, because dB squared is not small. It equals dt. Step 4 and 5. Substitute back and collect terms. Group everything multiplying dt and everything multiplying dB. And we arrive at Itô's lemma. df equals, open bracket, partial f over partial t, plus mu times partial f over partial x, plus 1/2 sigma squared times the second partial of f over x squared, close bracket, times dt, plus sigma times partial f over partial x, times dB. This term, 1/2 sigma squared times the second derivative of f. This is the Itô correction. This is the term that does not exist in classical calculus. This is the term that, when you ignore it, leads to mispriced derivatives and blown-up funds. In classical calculus, the chain rule is a first-order story. Itô's lemma is a second-order story because randomness lives at the second-order level. Nassim Taleb once wrote, "The problem with experts is that they do not know what they do not know." Pre-Itô quants didn't know they were missing a correction term. They were confidently, expensively wrong. Itô knew what the experts didn't know they didn't know. That's what genius looks like. Now let's use Itô's lemma to do something concrete. Derive the solution to the most important SDE in quantitative finance, geometric Brownian motion. The standard model for stock prices under the risk-neutral measure is ds equals mu SDT plus sigma SDB. The drift scales with the price, so we get percentage returns, not dollar returns. The diffusion also scales with price, so volatility is proportional, which is why we talk about 20% annual volatility rather than $20 per share. These are sample paths from this process. Notice they can go up or down, but they never touch zero, because the percentage changes scale with S, so you can never lose more than 100%. GBM respects limited liability. It's a feature. Now here's the question. What does the logarithm of S follow? Because log returns are what we actually compute in practice, and understanding their distribution gives us the analytical solution for S of t. Set f equal to log S. The partial derivative with respect to t is 0. F has no explicit time dependence. The first partial with respect to S is 1 over S. The second partial with respect to S is negative 1 over S squared. Plug these into Itô's lemma. The drift contribution gives us mu S times 1 over S, which is just mu, plus 1/2 sigma squared S squared times negative 1 over S squared, which gives negative 1/2 sigma squared. The diffusion contribution gives sigma S times 1 over S, which simplifies to sigma. The result is beautiful. D of log S equals mu minus 1/2 sigma squared, all times dt, plus sigma dB. This is just a constant coefficient SDE. Its solution is trivial. Log S is normally distributed with mean mu minus 1/2 sigma squared times t and variance sigma squared t, which means S itself is log normally distributed, and we can write out the explicit closed-form solution for S at any future time t. But look at the drift of a log return, mu minus 1/2 sigma squared. Not mu. There's a haircut, a drag. This is the volatility drag, and it's one of the most underappreciated facts in portfolio management. If your annual expected return is 10% and your annual volatility is 20%, your geometric mean compound return is not 10%, it's 8%. 2% per year, compounding quietly against you forever. Watch what happens over a long horizon. The arithmetic mean of S, which is S naught times e to the mu t, grows faster than the typical outcome. The median of S, S naught times e to the mu minus 1/2 sigma squared times t, is what most investors actually experience. And the gap between them widens every year. Itô's correction term isn't abstract mathematics. It's the gap between what a fund advertises and what investors actually receive. Before we get to Black-Scholes, we need one more piece, the Itô integral. Because just as differentiation doesn't work classically here, neither does integration. In classical calculus, the Riemann integral doesn't care where in each interval you evaluate the function. Left endpoint, right endpoint, midpoint. In the limit, they all give the same answer. The integral is path independent. Not here. When we integrate a process h with respect to Brownian motion, we are forced to use the left endpoint of each interval. Always. Not because it's convenient, because it's the only causally consistent choice. In financial terms, when you hold a position h of t over the interval from t to t plus dt, you must decide your position size before observing the Brownian shock in that interval. You can't know the future. The integral enforces this. This non-anticipating requirement means the integrand h must be adapted to the filtration. It can only use information available up to the current time t. If you use future information, you're not computing an Itô integral. You're cheating. And in trading, cheating is called insider trading. The Itô integral has two key properties. First, its expected value is 0, because Brownian increments are mean 0, and we're evaluating h before seeing them. No free lunch. Second, and this is the jewel, the Itô isometry. The variance of the stochastic integral equals the expected value of the integral of h squared. This is the stochastic analog of Parseval's theorem. If this feels complicated, it is. But the Itô integral is the only mathematically honest way to price a derivative. Every other approach is either an approximation or a prayer. The derivatives desk doesn't do prayers. Here it is. The application that made Itô a billionaire maker, even though he never cared about money. Black-Scholes. Derived live, from scratch, using Itô's lemma. Stock price S follows geometric Brownian motion. ds equals mu s dt plus sigma s dB. Option price V depends on S and T. We want to know what V is worth today. And here's the first remarkable thing. We're going to get the answer without ever knowing mu, the expected return of the stock. That's not a typo. Watch. Apply Itô's lemma to V of S and T. We get dV equals the bracket, partial V over partial T, plus mu S partial V over partial S, plus 1/2 sigma squared S squared times the second partial of V over S squared, close bracket, times dt, plus sigma S partial V over partial S, times dB. This describes how the option value changes over an instant. Now here's the cleverness. Construct a portfolio pi, long one option, short delta units of stock, where delta equals partial V over partial S, the options delta. The portfolio value is V minus delta times S. Compute DPI. It's dV minus delta times ds. Substitute Itô's dV and the GBM ds. Watch what happens to the dB terms. We have sigma S partial V over partial S times dB from the dV term. And we subtract partial V over partial S times sigma S dB from the delta ds term. These are identical. They cancel. Exactly. Completely. The randomness is gone. And look, mu, the drift, the expected return, it also cancels. The delta-hedged portfolio's dynamics depend on neither the expected return of the stock nor the random Brownian shock, both annihilated by the hedge. DPI equals partial V over partial T plus 1/2 sigma squared S squared times the second partial of V over S squared times dt. A deterministic expression. A riskless portfolio. In an efficient market, a riskless portfolio must earn exactly the risk-free rate R. Otherwise, there's an arbitrage, a money machine, and money machines don't persist. Set the two expressions for DPI equal and rearrange. And we have it. The Black-Scholes partial differential equation. Partial V over partial T plus our S times partial V over partial S plus 1/2 sigma squared S squared times the second partial of V over S squared minus RV equals 0. Each term has a name traders use every day. Theta, time decay. The gamma term, convexity, the curvature of the options value. And the discounting term. This PDE, subject to the terminal boundary condition V equals max of S minus K, 0, at expiry, gives the Black-Scholes formula. Notice D1 in the Black-Scholes formula contains 1/2 sigma squared. Itô's correction, embedded permanently in the price of every option traded on every exchange on Earth. Itô wrote 4 pages in 1944. In 1973, Black and Scholes weaponized them. In 1997, Scholes won the Nobel Prize. Itô won the Gauss Prize in 2006, mathematics equivalent. The market paid better. One thing nobody tells you in a quant course. Itô's convention is not the only one. There's a parallel universe called Stratonovich calculus that physicists and engineers often prefer, and understanding why finance rejects it is important. The difference is subtle but profound. Itô uses the left endpoint of each time interval, We evaluate H before seeing the Brownian shock. Stratonovich uses the midpoint, which requires partial information about the future. This gives Stratonovich a beautiful property. The classical chain rule holds without any correction term. Newton's ghost is happy, but for finance, Stratonovich is inadmissible. Using the midpoint means using information that doesn't exist yet at the time you need to make a trading decision. It violates causality. It's the mathematical equivalent of front-running. Ito's convention enforces the reality constraint. You can only act on what you know now. The two integrals differ by exactly 1/2 the integral of the derivative of h with respect to b. You can always convert between them. But in financial modeling, Itô is not a preference. It's a constraint imposed by the arrow of time. The Itô correction isn't an inconvenience. It's the mathematical price of operating in a world where time flows in only one direction and information arrives sequentially, which is, inconveniently, the world we live in. Let's land this plane with 4 truths. The version the textbooks are too polite to state directly. First, every time you ignore the Itô correction, you are systematically mispricing convexity. Not occasionally, not under edge cases. Systematically. Every model without the second-order term understates the value of options, underestimates the cost of hedging, and overstates the performance of leverage strategies. The correction is not optional. Second, volatility drag is real money. If your fund earns a 12% expected return with 25% volatility, your geometric compound return is not 12%. It's 8.875%. You are surrendering over 3% per year to the Itô correction. Compounding over 20 years, that's the difference between retiring and working until you're 70. Nobody told you this at the fundraise. Third, Ito's lemma is the reason delta hedging works. It's the reason Black-Scholes exists. It's the mathematical foundation of a $600 trillion market. This isn't an academic curiosity. This is the bedrock of modern finance. And it lives in 4 pages written by a Japanese mathematician during World War II. Fourth, and most practical, in a quant interview, you will be asked about this. Not the formula, the derivation. Knowing that dB squared equals dt and being able to explain why it can't be discarded is the signal that separates candidates who understand the mathematics from those who memorized it. The Itô correction is the differentiator. Literally. Nassim Taleb wrote in Anti-Fragile. Anything that has been around for a long time has proven its anti-fragility. Ito's lemma has been around since 1944. Through every market crash, every quantitative revolution, every Nobel Prize in economics, it's still here. Still right. Still running every derivatives desk on Earth. Learn it. Own it. It might be the most important 4 pages ever written. That's episode 2 of Quantifeia. We covered the complete story, from Brownian motion's axioms, through quadratic variation and why dB squared equals dt and cannot be thrown away, through the full derivation of Ito's lemma, through geometric Brownian motion and the volatility drag, through the Itô integral and its isometry, and finally to Black-Scholes, derived from scratch, live in real time. 2 books belong on your desk after this video. Shreve's Stochastic Calculus for Finance 2, the rigorous version of everything we covered, chapters 3 and 4 specifically, and Paul Wilmot on quantitative finance, the applied version, with the intuition and the worked examples. Both links are in the description. Next week, we take the Black-Scholes formula and extract its weapons, delta, gamma, vega, theta, rho, the Greeks. We'll build every single one from first principles, show you what they mean economically, and explain why gamma exposure is the most dangerous thing a derivatives desk can run. Don't miss it. One final thing. Here's a challenge. Using today's tools, derive the Itô correction for f of s equals s squared. If your expected return is mu and your vol is sigma, what does d of s squared equal? first correct full derivation in the comments gets pinned for a week. Subscribe. Share this with one person studying for a quant interview. It'll probably get them the job. This is Quantifea.